Feel the rhythm, feel the rhyme, get on up, it's game dev time. I cannot believe I decided it was a good idea to open with that. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games. Let's talk about 3D collisions in GameMaker. So this is going to be the beginning of what I believe I called Act 2 the last time of this 3D collisions in GameMaker series. The first act, if you have not seen it already, was all about figuring out collisions between basic points, figuring out if basic shapes were intersecting in GameMaker, including the point, the sphere, the axis allowing bounding box, which in common parlance you might just call a brick, and the plane, as well as a raycast and line segment cast into each of these shapes. And Act 2 is going to be all about bringing triangles into the mix. We are going to be working out intersections between triangles and shapes, triangles and rays and line segments, and of course triangles and other triangles, as well as 3D models built out of lists of triangles, and ways that you might want to organize triangle data in order to speed it up. Then at the end of the series, and I haven't decided exactly what I want this to look like yet, but I do want to do another one of those collision world videos, so that we can see how this might work in an actual game. Okay, so if we look back at this test program, I have gone ahead and added a couple more test shapes for triangles, and they don't really do anything yet, they don't detect collision yet. I haven't even written any code to allow you to move these around on the screen with the arrow keys so that you can test them in different locations the way I have with the other shapes. We'll get to all that in due time. First, let me just quickly show you what this looks like. We have the test triangle. A triangle is composed of 3 points, 3 vector 3s, 3 points in space, and then instead of the test class using a default shape loaded from the file, we are just going to be building a triangle vertex buffer out of those 3 points. They're lying flat on the ground. The normals for the triangle for lighting purposes are just pointing straight up in the air, 0, 0, 1. I will get to generating triangle normals soon enough. That is something that may turn out to be fairly important fairly soon. And then, of course, down here, when you come to draw the triangle, you just vertex submit it, set the matrix to the identity matrix. Backface culling is of course, turned off because I don't want these triangles to be double-sided, but that's not going to be the focus of today's video. If you have not yet watched Act 1 of this 3D collision series, I highly recommend going and doing that. I'm going to be operating under the assumption that everybody who watches these videos from here on out has and is familiar with things such as the vector class and some of the other practices that I've been following, naming conventions and whatnot. I'll have links to the beginning of the playlist in the video description and in a card and that sort of thing. Otherwise, assuming that everybody has gone and done that, let me open up the call_shapes code file. We are just under 300 lines of code in this file. This is going to be quite a bit longer by the end of Act 2. Let's start out by defining a triangle. So I'm going to say function call triangle. This is going to be a constructor function for triangles. Triangles, as you all hopefully know, are composed of 3 vertices, 3 points in space. I'm going to name those A, B, and C in the constructor. Of course, the constructor has to be actually marked as a constructor. And then we are going to be, the first thing that we're going to do is self.a is going to be A, self.b is going to be B, self.c is going to be C. We are going to take these constructor parameters and save them to instance variables of this triangle struct. That's all the information that defines a triangle with an asterisk on it. I'll get to the surface normal later. But next, I'm going to define a couple functions. One is going to be static checkpoint, and that's going to be equal to function which takes a point as a parameter. I'll fill in the body of that function momentarily. Next, we're going to do something that should look very familiar to those of you who have watched the first 8 or so videos in the series. Check sphere. It's going to be a function that takes a sphere as a parameter. Check ab for the axis aligned bounding box, and check plane for the plane, checking collision between a triangle and a plane. Next, there is going to also be static triangle. That's going to be a function which takes a triangle as a parameter. We're going to also have check ray and check line. Raycasting functions, these are going to take a slightly different form. In addition to just the ray instance of a struct that we're going to take as an input parameter, there's also the hit info, as with raycasts against the other shapes. Again, we will fill that in when the time comes, and check line is going to check for an intersection between a triangle and a line segment. And then, of course, we need equivalent functions in some of the other basic shapes. So this is in call point. We're going to define static triangle is going to be a function which takes a triangle as an input parameter. We will fill that in when the time comes, as I said, and all of the other basic shapes are also going to take. And I'll put this function beneath check plane and above check ray and all of these classes. The sphere is also going to have a check triangle function. Really should call them methods. The axis align bounding box is going to have a check triangle method. The plane is going to have a check triangle method, and that brings us back to where we started. And also the other rays. So I will give the ray a check triangle method. This is going to also take a hit info struct as a parameter, but we'll worry about that later. And check line. Okay. So these are the functions that we're going to be filling out in the future over the course of the next several videos. I had that progress matrix in Act 1, and I will have another project. That's suddenly a hard word to say. I will have another progress matrix for Act 2. In addition to basic triangles, which we're going to be checking each of these shapes against in Act 2, we're also going to have, as I think I mentioned earlier, meshes composed of a list of triangles. So this version of the project's matrix is going to have cells for both triangles and triangle meshes, and we'll get to each of those things in due time. So there's a couple other helpful functions that I'll be wanting. One is going to be, and I mentioned this one a minute ago, static get normal. That's going to be a function. There's also going to be static method. I'm suddenly messing up my terminology. I think I was fairly consistent calling them methods in Act 1, and I need to get back in the habit of that in Act 2. There's also going to be nearest point. It's going to be a function, and this is going to take a vec3 as an input, and that's going to find the nearest point on the triangle to the vector3 that was specified. We will be filling that in today. There's also going to be static get plane, which is going to be a function that we're going to be getting into. So first, the first thing that I'm going to do, get normal. If you've ever used a 3D modeling tool like Blender or any of the other 3D modeling tools out there, the surface normals for each triangle will be set more or less automatically by the 3D modeling software. And you generally, if you're working with 3D models, don't have to worry about calculating the normals for each triangle yourself, whether that's a flat normal for the triangle or a smooth normal for each vertex. For the purposes of 3D collisions, we're going to be calculating the normals for triangles ourselves. Calculating the surface normal for a triangle is actually fairly straightforward. Triangle surface normals are just the vector that's pointing perpendicularly out of the surface of the triangle. And we have a handy tool for figuring out a vector that is perpendicular to two other vectors, and that is the cross product. And you would think I would have this memorized by now, considering how many times I've done it, but I'm consulting my notes anyway, just to be sure. First, I'm going to say var diff ab is going to be self.b.sub self.a. Secondly, var diff a c is going to be self.c.sub self.a. These two vectors are going to represent the direction from point A to point B and from point A to point C. And we are going to, we have these two vectors, we are going to generate the surface normal by calculating a little cross product. Return diff AB dot cross diff AC. And this vector is not guaranteed to be normalized, so we're going to normalize it. This function can fail if, for example, all three of the points composing the triangle are the same, because then you won't be able to really calculate a cross product for that. You'll have the zero vector, and then when you try to normalize the zero vector, bad things will happen. But we're going to assume that when you create a triangle like this, you are not going to have a triangle with zero surface area. I may go into more depth about how this works. I do want to make videos in the future about generating surface normals, both flat and smooth for 3D models that you may generate in real time, but that's another story for another time. Next, nearest point. This is going to actually be a little bit more involved. This is going to actually depend on the getPlane method, so I guess it'll make sense to work on that one first. Triangles, a handy property of triangles is that all three of the points that compose a triangle, any 3 points that you can imagine, are all going to be coplanar. There is, for any triangle that is ever going to exist, you will be able to create a plane that runs through each of those points. And that is going to have a few applications when it comes to 3D collision checks with triangles. For those of you watching this who are still in high school, the next time one of your classmates gets up and says something to the effect of, "Who needs math? I'm never going to need any of this in real life. Who cares about planes and geometries and all that weird stuff?" You can officially get up and tell them that you've used geometry in your real life and that they should be quiet. So planes are defined by a surface normal and a distance from the origin. The surface normal the surface normal of the triangle we have var norm is going to equal self.get normal. I'm suddenly losing track of my keyboard. That is the method that we just defined a minute ago. As for the distance to the origin, let's say var dist is going to equal, and a handy thing that you can do with surface normals and dot products is norm dot against self dot a. If you take the surface normal of this triangle and if you take the dot product of that against one of the points of the triangle, against point A, in this case, where am I? Page up, page down. If you take the normal and dot product that against self dot a, you're going to get the distance from the origin. Handy little property of math. And as for the plane that we're building, we can say return new call plane. And that is going to take norm as its normal and dist as its distance. And this is going to be getting a plane from a triangle. Next, let us actually do nearest point now. So I'm going to start out with the nearest point function by saying var plane is going to equal self.get plane. Again, that's the function that we just defined up here. The next thing that we're going to do is we're going to find the nearest point between the input point, the input vector 3, and the plane. So we can say var nearest to plane is going to be plane dot... Was it nearest point? Nearest point? Pretty sure I called it nearest point. I'm using the right terminology here, right? Alright, it is nearest point. So we can start off by getting the nearest point to the plane that runs through each of the points on the triangle. Now, if this nearest point to the plane is already inside the triangle, then that's just it. That's our nearest point. The nearest point between this vector 3 and the triangle is going to be the vector 3 itself. And we don't need to do any further work. And I'm going to be doing a tiny bit of sequence breaking here and saying, we can say if self.checkPoint, and the point that we're going to pass it is just going to be a call point composed of nearest to plane, because each of the shape checking methods, including checkpoint, expects to see a one of the collision shape wrappers. So we're going to take that vector 3 and we're going to wrap it inside a call point.
Hey.
Anyway, if this point is already inside the triangle, then we're just going to return nearest to plane. Triangle checkpoint has yet to be implemented. That's this method up here. We will be getting to that in the next video. But since I do not need triangle's nearest point method implemented for anything that I want to do in the rest of this video, then I think this is an okay concession to make. Next, if the point nearest to the plane is not already inside the triangle, there is something else that we can do, and that is we can break the triangle into 3 lines, which represent the edges, and we can say new call line. This is going to take a starting point and an ending point, and we're going to do this 3 times. One of them is going to be a line from triangles self.a to self.b. Another one is going to be a call line between self.b and self.c. And the third is going to be a new call line between self.c and self.a. If the nearest point is not already inside the triangle, we can figure out the nearest point to the triangle by figuring out the nearest point to any of its edges, represented by a line segment. Let me give these names. Let's call this one var line AB. It's going to be that. Var line BC is going to be that. And var line CA is going to be that. This probably is going to look very, very familiar to anyone who's worked with triangles in geometry, trigonometry, or both. I hope nobody has been too traumatized by this sort of thing from school, because we are going to be doing a lot in the coming videos with this sort of notation, line A, B, and such. Anyway, next, as I said, we can figure out the nearest point to each of these lines. So we can say var nearest to AB is going to be line AB dot nearest point. The input vector, the input point. We can do this 3 more times. We are going to have line BC and line CA, and we're going to use the appropriate line segment in each of these cases respectively. Next, we're going to figure out the distance between each of these nearest points and the lines. And the nearest point to the triangle is going to be the overall closest one of these. So we can say var dist AB is going to be vec3 dot distance 2 nearest to AB. Going to do this again 3 times, dist BC and dist CA. And we're going to be checking the distance to the nearest point to line AB, the nearest point to line BC, and the nearest point to line CA. Okay, and then if dist AB is less than dist BC and dist AB is less than dist CA, then this is going to mean that the nearest to AB point is going to be the nearest point to the triangle. Next, if dist BC is less than dist CA, and I believe at this point this can be proven redundant, but I'm also going to say dist BC is less than dist AB, just so that this if statement looks like the one above it. But I believe this this part of the expression here is redundant. Not going to spend time trying to mathematically prove that. Anyway, we can return nearest to BC, and if all else fails, if neither of these points are the nearest to the triangle, then what's left is nearest to CA as our nearest point to the triangle. Okay, that was a bit longer than the previous 2 methods that I implemented, but it's going to be coming in useful for some things in the next coming videos. If you remember the point and sphere checks from Act 1, you probably have a pretty good idea of what this is going to be used for. But I think that's going to do it for now. We have defined a triangle, we have defined the surface normal of the triangle, the plane of the triangle, and the nearest point to the triangle. Actually, while I'm here, because it would be a shame if I had to do this, if I forgot to do this now and had to do it later. In the call test triangle, self.data, we can assign this a value of new call triangle, and the A, B, and C points are going to be P1, P2, and P3. It's semi-common for people to refer to triangles in terms of both A, B, and C points and P1, P2, P3. I'm going with A, B, C as my 3 points in the triangle, mostly so that I can do things like saying like line AB nearest to BC, that sort of thing, because that's a little bit less awkward than saying like line P1, P2, at least in my opinion. I guess something like line 1, 2 would be just as concise. Anyway, this is going to be defining the collision data for this test triangle, and just for good measure, instead of hard coding nx, ny, and nz to be 0, 0, and 1, we can actually get the triangle's normal from the getNormal method, and we can say nx is going to be norm.x, ny is going to be norm.y, and z is going to be norm.z. And that way, if later on when we generate triangles that are not just lying flat on the ground, then we can calculate the surface normals like this. And in fact, I'm just going to run this now. If I were to generate some triangles, let me zoom in. That's out. Let me zoom in. If I were to generate some triangles. Okay, our surface normal is still looking good. It's still pointing straight up. The top is being fully illuminated. And if I were to randomly generate a z-coordinate of random range between, let's say, -20 and 20, then the surface normal should be correctly calculated, no matter how the triangle is oriented. And let's see, let me find a decent shape. All right, there we go. So this triangle is decently big. We can get a good look at it. It's fully lit, and we can see that the surface normal is pointing in the right direction. It's more or less head on to the light source. If I were to generate one that's lying a little bit more turned away from the light source, we can see it'll be dark. It's maybe not what we want, but it's maybe real quick. Let me go into the shader and bump up the minimum rather, light value so that we can at least see a little bit of the unshaded sides of triangles. Okay. We're pointing the opposite way from the light source now, and we're still semi-lit, just not in direct sunlight. Okay. Let me make this a GitHub commit. Let me actually make this several GitHub commits. First, we're going to define the triangle shape. And then we can, I'm just going to say I updated the demo a little bit. Okay. So, with that, I hope you all found that useful. We're going to be doing something with actual collisions in the next video. I'm going to tag and create a release. I've been tagging releases, right? It looks like I have been. This is going to be 0.9. I'll bump the number up to 1.0, probably at the end of Act 2. I won't be continuing. I won't start Act 2 off with 1.0 because I feel like we're still not really complete yet. But I think once we have a triangle hierarchy, then I'll officially call that 1.0. Anyway, let's create that tag. I will create a release on tag 0.9 pre-release. So if you want the code for this, look for this GitHub repository down in the video description, specifically if you're looking for what I did today, look for the 0.9 release. I have a Patreon, so if you want to contribute towards these videos being made, look for the links to that in all the usual places. Otherwise, I try to post about 2 game dev videos a week, one tutorial such as this, and one Let's Make a Tower Defense game. I hope you all find this useful, and I will see you all later. Special thanks to Connor, Edward Holt, Emily Koyo, Halo Factory, Posho, Sindra Larson, Tusk, and Zenith for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.